Hello and welcome to my presentation on the history of math, part 3. We begin during the Renaissance. At this period of time, there was great commercial success in Italy, and with all this new influx from new trade, it called for the creation of basically modern accounting and a new class of accountants, or the abacus, who had a focus on the practical and economical uses of math. The decimal system was fully embraced during this period, and many modern symbols that we still use today, such as plus, minus, and square root, were introduced. These can be seen in Chris Rudolph's Cos, which was the first German algebra text, and it included his work on the theory of exponents, as can be seen on the right. Some other new men for this new era was Maestro Dardi, who extended the work in algebra that the Muslims did, but it extended it far beyond to higher order equations. He specifically worked in cubic equations, but the solution he produced was not very applicable. Another new man of this era, an abacus, you could say, was Robert Recorde, who wrote the first algebra text in England. In his book, he expressed higher degree powers in terms of squares and sine, and introduced the modern equal sign. Overall, this era saw much innovation from what the Muslims and Greeks did. The Italians made many innovations in their study of algebra, and real progress over the previous Islamic translations they inherited. One of these men was Girolamo Cardano. Although he didn't necessarily invent the solution to the cubic equation, he was very influential because he was the one who revealed its secret. There's a whole story behind that, but I won't go into that right now. In addition to publishing the Ars Magna, he developed conditions for true or fictitious solutions, and his pupil Ferrari continued his work and solved fourth power equations. Bombelli had the most systemic approach of his era, shown in his book L'Algebra, and he made many breakthroughs, introducing new symbols like parentheses, computational rules by analogy, and most notably, imaginary numbers and complex numbers. One of the last major innovations in this area of algebra was by Francis Viète, with his creation of algebraic symbolism and analysis that revamped the original method seen in Greece, where instead of verbal descriptions and numerical examples, he used letters for known constants. This made formulas possible, and he transitioned to studying in equations form. We begin to see Italians really make math their own, with their unique use of trigonometry for art. Along with the usual uses for navigation and astronomy in this age of exploration, there are also people like Leon Battista Alberti, who used trigonometry for added realism and better perspective in their art, as can be seen on his right in his guide on how to write tiled floors in this pyramid shape. Regiomontanus, or Johannes Muller, wrote the first pure trig textbook. It was after the Greek style in their geometric fashion, beginning with definitions and axioms, very similar to Euclid. However, he expanded upon it by proving the law of sines using spherical triangles. In addition, he also wrote on plane triangles. He really represented the continuation of the Greek study of geometry, but with the innovation of the Renaissance. Simon Stevin, another great mathematician of this era, pushed for decimal fractions and did decimal operations like division, and eliminated the previous Greek idea of the distinction between number and magnitude, in effect giving us our current concept of numbers, and represented while they are continuing the study of Greek, they're also stepping away and making their own path in mathematics. We reach my favorite subject, astronomy. Of the many great innovations of this era, the greatest were in astronomy, and it led to the modern form. Copernicus put forth the heliocentric model, where this was in division to the original church's view that the Earth was the center of the universe, but it was agreed upon by many famous scholars like Galileo Galilei. Johannes Kepler was another great astronomer of this era, and he used empirical data and conics to accurately describe planetary motion across his three laws. The most important discovery was that planets orbit in ellipses and not perfect circles, as was thought beforehand. Probably the greatest mathematical related innovation that was caused by a pursuit of understanding astronomy better was logarithms. Jack Navier invented logarithms to have more efficient calculations for astronomy. Specifically, he focused on logarithms related to sines, and he put them in tables. However, his definition of logarithm was very different to the modern one. Instead of being the opposite of an exponent, he imagined 2 points moving along 2 lines. Point P moved at a constant speed, 0 to B, 2 to B. However, point P or point Q speed decreased according to a geometric sequence where r is the line length, slowly going slower and slower. He called these distances they traveled logarithms. As we transitioned to the 17th century in Europe, the printing press became more popular and knowledge became easier to attain and spread amongst peers, and a community of scholars was formed among the many European universities. We also saw the creation of the field of analytic geometry, as Europeans have mastered algebra at this point. Albert Gerard, for instance, had the fundamental theorem of algebra. The two big names in analytic geometry are Pierre de Fermat and Descartes. Pierre de Fermat found the solution to two variable algebra problems in using lines and curves, and saw how they reduced to one of Apollonius's conics. He also assisted in many areas of mathematics, such as number theory, probability, and even the beginning of calculus. Descartes had a similar yet different approach to this subject. He used curves to create equations. This can be seen on the right, where he tries to find the solution to the quadratic equation using circles. He can draw additional lines to form different triangles and then use the Pythagorean theorem to find the length of those lines, and it eventually finds the solution. He is also the origin of the x and y coordinate system that we still use today, and he was the first to give us the factor theorem. Probability has its origin in gambling, specifically being able to calculate the odds of winning a game, or how to divvy up a pot when a series of games was not entirely finished. The foremost expert in this field was Blaise Pascal, who innovated probability with the creation of many different formulas, specifically the creation of his triangle, which showed up in other parts of history, but is very important. As can be seen on the right, each number in the pyramid is the sum of those that came before. Like 3 is the sum of 1 and 2. He also did projective geometry and mathematical induction. Another part of this field was Christian Huygens, who wrote the first probability text. He was concerned with the expected value. For instance, with his formula, you could find the expected value of a game if you could win A amount with probability B. This could be such as rolling a 6 on a dice 4 times in a row. Now we enter the late period of Western Europe development, before everything's changed. Throughout the many innovations, specifically analytic geometry, there were many new examples of curves and solids to explore. Mathematicians of this time sought for and discovered new ways to finding extrema, constructing tangents and areas and volumes. Many familiar names pursued this goal, for Matt devised a method for finding tangents and extrema based off Viente, and even used double roots to find the maximum. He specifically used an approximation using many rectangles to find the area under a curve. Descartes created the method of normals, which you can find a circle that's tangent to a curve and the circle's radius is normal to it. This method was later enhanced by Johann Huyghe and fixes the messy algebra. Overall, we are just on the brink of Europe's greatest discovery so far, calculus.